Okay, so welcome to the new world. I'm very glad that we have, first of all, Zhengfeng here as presenter and a large list of people online. This is a new experiment, trying to keep our academic collaborations and exchanges going in this crazy period. Before Zhengfeng takes over and I introduce him, we need a couple of rules to make this work. And that is the request, please mute yourself during the presentation and also turn off video just to not burn the internet. After when we have the Q&A, of course, you speak up, turn on the video, and then we try to have like an interactive discussion. Or if there's something pressing during the talk you really need to raise, then go for that. So with that being said, I would like to welcome Zhengfeng who is currently a professor in the Center of Quantum Software and Information at UTS. He received his PhD from Tsinghua University in 2007, did a postdoc at the esteemed Perimeter Institute for Graphical Physics and Institute for Quantum Computing in Waterloo. And his research is currently focusing on quantum algorithm and complexity theory, quantum post-quantum cryptography, and quantum computer science in general. It's a great pleasure. Zhengfeng, please take it away with this experiment.
Okay. Thank you, Sven, for the introduction. It's also my first Zoom talk. And I hope that everyone can hear me. I'll talk about a recent result that colleagues and we worked on the complexity of Bayer inequalities. And so the title is called Spooky Complexity at a Distance. It's a complexity theory result, but it uses a lot of quantum information and physics ideas. And so alternatively, the title could be like the paper has MIP star equals RE, and it's like two complexity classes. MIP star is a complexity class, RE another class, and the result appeared early this year on arXiv, and it's a joint work with Anand Natarajan, Thomas Wittig, John Wright, and Henry Yuan. So the first part, I'll quickly guide you through the history of the problem. So when the result came out, I guess it caused some of the excitement in the community, and not every people understand why the result is interesting. And I guess to understand that, you have to understand the connection that the problem has to many areas that the problem connects to. And so this is the first part of the talk. So there are three areas that this will be related to. One is computer science. So in computer science, basically the area started in the 30s. And now at that time, the people start to think about the idea of what is computation, how to define computation. And there are several models of equivalent models of computation, and Turing machine is one of them. So, and also Turing, in his seminal paper, he proposed this halting problem that's been used in our work. He basically says that if given a Turing machine or an algorithm, whether the machine terminates or not is undecidable. There's no algorithm for that problem. And later, because now you have like computers, and efficient computation becomes an important concept. So the complexity theory was developed in later years, in the 70s. And one important area of that research is proof verifications through the so-called computational lens. You think of computation as sort of a proof of certain facts, and different models in that proof verification framework proposed, like MIP MIP, this a long list of combinations of capital letters. These are so-called complexity classes, and they are a class of problems that be defined in that model of proof verification. You can see the MIP, which is very close to the class that we use in title MIP star, is one of them, and we will come to that later. And I guess like in the line of research, the PCP theorems come out of the study of NP and multi-proof interactive proof systems is one of the most important achievements of complexity theory. Sometimes it's referred to as the crowning jewel of complexity theory. That's another technique that we relied on in our proof, essentially. And so because this proof verification concept is so important to our approach to the problem, we will first introduce the concept in more detail. Basically, the situation that you have a prover and a verifier. Sometimes it's multiple provers, but you have a verifier, and the prover's goal is to convince the verifier of certain facts, that maybe a graph is colorable, some problem has a yes solution to the problem. You have a bunch of equations, there's a solution, problem like that. And the prover wants to convince the verifier of the facts. And there are two conditions that we should consider. One is called completeness condition, and the other is called the soundness condition. The completeness condition says that if the proof the statement is true, then the prover should be able to convince the verifier. But we also require that the soundness requirement, meaning that if the proof that the statement is not true, then there should be no proof. No matter what the prover does, there should be no cheating strategy for the prover, so that the verifier would accept. And so in this first model, if you can see here, you see follow the red dots, then that's the model where you have like a prover who send the message to the verifier classically, and the verifier can decide whether to accept or not. Like you have a paper and you just verify the correctness of the claim. And in complexity theory, we call this class MP, and for non-deterministic polynomial time, and it's a big open problem, like how to characterize this class, whether it's P or not. And that we don't know. But later on, people studied different variations of this proof verification model. So instead of like having a written proof, you can have a prover and talking to the verifier. So the verifier and prover can exchange questions. And in the end, the verifier would accept or reject. And that's called interactive proof, so letter IP. Interesting, we do know the power of this interactive model, and it's a well-known complexity theory result in the 90s that IP equals to P-space. P-space is a class of problem that you can solve with polynomial amount of space. So you can see that these two classes, like IP and P-space, are very different, but it turns out that they characterize the same set of problems that we can solve. And the class of MIP is a more like further generalization where you have two provers. And in that model, the two provers are talking to the verifier, but the provers cannot talk to each other. Like Alice cannot talk to Bob, and Bob cannot talk to Alice. Otherwise, they would behave like a single prover. So that's a two-prover model. And the intuition that having an extra prover would help you, like help the provers to convince more statements, is that you can think of a situation where you have interrogation of criminals in separate rooms, and you can cross-check whether they give the consistent answers. And as it turns out that actually we do have a characterization of MIP in terms of complexity class, another standard class called NX, which is like an exponential follow-up version of MP, and these two are the same, and you know that it's different from MP. So starting from this MP and adding an interaction, adding a second prover, we do have increased the power of what the prover can prove to the verifier. So That's a very interesting step. And so this class of MIP, we will come back to this class later, and we'll consider quantum analogs for this class. But for now, in complexity theory, the next step is actually development of probabilistically checkable proof. It's based on the result of the result of MIP equals NX. Somehow downsizing the complexity class would give you the PCP theorem. And so the PCP theorem is a model where you have verifier and a written proof. And then the verifier would flip some random coins and choose to where to look in the proof. So the parameter, I have like a parameter R, and it's randomness that the verifier uses. And Q is the number of bits that you would read from the proof. So think of the proof here as n bit strings. And like in order to index all the bits, you would need log n. Like in order for the verifier to communicate to decide where to look, you need log n bits to specify the position, right? The amazing thing of the PCP theorem is that it says that MP equals PCP of big O of log n and big O of 1. Basically, it says that you would only need to look constant number of bits in that n-bit string, and you will be able to verify whether the statement is true or not. Like remember, you have like a problem in MP whether a graph is recolorable. You don't need to look at all the vertices and check all the constraints are being satisfied. We would only need to look at constant fraction, the constant number of places to verify that the statement is true, and that's quite counterintuitive and a very powerful idea. So if you look at the history, like from MP, we generalized to IP and MIP, and then develop PCP theorem, and it gives an alternative calculation of MP. And also the PCP theorem is a very powerful tool that it's not only a theoretical result, it has applications in the applications of computation, and also a very important tool in hardness of approximation, like problems whether I don't want to optimize, have the optimal value, but like have a constant approximation of the problem. And the quantum analogs of these classes, like MP, IP, are important classes that we study in quantum complexity theory. I guess like for PCP, there's a very long-standing open problem called quantum PCP conjecture, whether the similar situation still holds in the Hamiltonian complexity theory is a wide open question. So that's what we would review about interactive proofs. And coming back to the three different motivation or different background this research relates to, the other motivation that we have is for physics. Again, in the 30s, like Einstein, Tsirelson, they had this famous paper of EPR paradox. Basically, they would question the completeness of quantum theory and the behavior of entanglement, even like two single spins would behave very strangely, that Einstein would call it spooky action at a distance. And this is also where our title is coming from. So it's not only you can have spooky actions at distance. If you look at the complexity level, it's also very spooky results that we have. And then in the 60s, John Bale came up with a very revolutionary idea of Bale inequality. So basically, it's a very simple setup. You can test whether the world is quantum or classical. you can do experiment and see whether there's a number of classically it's less than 2. Otherwise, it's higher. You can do experiments, and I guess nowadays there are many experiments being done, and people tend to believe that the world is quantum. And also to understand the structures of this kind of inequalities, Tsirelson pioneered this area, and basically, like if you think of Bayer inequalities, it's like the optimization. You have like the correlation set here is the classical correlation set, and this bigger region is quantum. You would be able to characterize, so a Bayer inequality is like a hyperplane or line here, and that's basically the classical region that you can reach. But Tsirelson asked, like, what is the boundary, or how can you optimize over the quantum set? And he also pioneered the study of special class of inequalities, which relates to the XOR, like two-player XOR games later found interesting in the community. And along the way, he proposed a very interesting problem, which was now called, known as Tsirelson's problem. And it asks whether finite quantum systems can approximate infinite systems. And so on a very high level. And we will come back to that problem later in this talk, like how we state this more rigorously. So that's for physics. And the problem also has connections in mathematics. Again, in the 30s, John von Neumann studied the algebra structure of operators, and later on it's called von Neumann algebras. And I guess it's trying to lay the foundation for quantum theory and quantum field theory. And so in mathematics, people try to understand these definitions and try to classify the object. And here's like von Neumann algebra. And there have been different types of algebras that have been identified, like type 1, type 2, and type 3. So it has been like even in the 70s, Alan Kahn studied this problem, and I guess that's where this another connection for us is occurring. He like in his paper, there's a very brief mentioning of a conjecture or problem called Combs embedding problem, and says that whether every type 2-1 factor on a separable paper space can be embedded into some ultra power of hyperfinite type 1-2 factors. So if you're not familiar with this research area, it doesn't really mean much to you, but I guess it has been later on understood that it's an important problem in operator algebra, and in recent years there have been many conferences dedicated to this single problem, and not only because it's a single problem, also because it's a problem that have a lot of different equivalent characterizations. One prominent example is Kutzberg's QWEP conjecture in sister algebras. And also in quantum information community, it's been known that Tsirelson's problem is also equivalent to Combs embedding problem. So if they have positive answers, if and only if the other one has a positive answer. So that's the connection. So to summarize the brief history that we've been talking about in physics, in computer science, in mathematics, there are problems that are related, like Tsirelson's problem and Combs embedding conjecture. But like computer science, it doesn't really has anything to do with these two different, at least it looks like very remote. But nevertheless, result that we have, you can think of it as using computer science techniques, also quantum information techniques, but in the end to give answers to questions in physics and mathematics. So I guess that's the first part of the talk. Now I want to give you a more closer look at the problem. So the class that, the object that we are studying is called quantum multi-prover interactive proofs. So there will be, again, like in MIP, I have two provers and a verifier. The difference is now provers can share entanglement. Still the messages that the exchange is classical, and that's the class MIP star. And the difference that you can see with or without the star is whether you have entanglement or whether you have only shared randomness. This is like a very simple observation, but I think it's the importance of this connection is that now we can try to understand this model, like or Bayesian inequalities, using a lot of techniques that we have from the classical literature of computer science, where this two-proof verification model has been studied. So in this talk, we will use the language of non-local games to specify the game. We have two sets: the question set X and Y, and also we have distribution mu over the question sets, and then the decider D. So given the questions and answers, you would be able to decide whether to accept or reject. So all these X and Y, A, B, and D, they are finite. These are finite sets. These are predicated on the finite sets. So in other words, the game itself is a finite structure, and that's an important thing to keep in mind. And given the game, we can study strategies of the provers, and we'll consider actually two types of strategies. One is called entangled strategy. In that case, you would allow the players to share a state, and then they will have a set of measurements. So AXA will be the measurement that Alice uses for question X, and outcome, measurement outcome would be A. So these are POVMs. But like in this setting, the state is in Alice and Bob's tensor product, Hilbert spaces. And now the value of the game is, intuitively, it's the maximum winning probability of the players. So you start with the state and you measure the operators, then that's a probability of conditioning on question being X and Y. You would get the probability you get A and B. And we take expectation, because that's a random procedure. So expectation of the questions, and then you take a summation over the answers that are accepted by the decider. And you take the soup of all strategies, like the strategies specifying the state and POVM, but you want to the prover to use the optimal strategy. So that's a number, and because these are like numbers in 0 and 1, you can usually see that's a number in 0 and 1. And basically the class that we are focusing on, MIP star, is the problem of approximating that value given the game. Maybe you have like an ipsilon error you can tolerate. I want you give me a value that's ipsilon away from the optimum value, and that's basically the class is about. In like when you specify the sizes of the messages of the game. So that's one type of strategy we will consider. The other type of strategy is called commuting operator strategy. And so it looks very similar. The only difference is that you have now a single Hilbert space. And so you don't have tensor structure. But in order to say that Alice and Bob are they are space like separated, then we would require that Alice's operator and Bob's operator are commuting for all A, B, and X, Y. So that's a new requirement that we have. So that's called commuting operator. So the commuting operator value is again the superman of the strategies, expectation, summation, roughly the same expression, but you don't have the tensor structure like tensor product anymore. So that's another value of a game. So given a game, I can study this commuting operator value. And Tsirelson's problem is asking whether these two values are always the same for all games. And one thing that we should mention is if you consider finite Hilbert spaces H here, then the value would exactly equal to the entangled value with the star, because for all finite dimensional Hilbert spaces, once you have the commuting structure, you can show that it's actually a direct sum of tensor structure. But we don't know what happens when the space H is infinite dimensional, and that's why we can see that Tsirelson's problem is asking whether we can approximate infinite dimensional systems with finite ones. Okay, so so now we have defined the model and two different values, and we've been able to talk about the Tsirelson's problem in terms of whether these two values are the same. The next thing is briefly telling you what we know about the complexity of computing these values. Now, so we would introduce two algorithms. The first algorithm is essentially trivial. Basically, what it does is to approximate, or to try to approximate this value. What you can do is to do some exhaustive search for better and better strategies with better precisions. So you fix some dimension of the Hilbert space and make a very fine epsilon network epsilon net in that strategy of the game. Then you can know that the value would be very close to that. Given if there's a good value within that dimension, then the algorithm 1 would give you a good answer. And what you can see is that you can have a sequence of values approaching the quantum value from below. So like here, the algorithm 1, if you run it, it doesn't give you an efficient algorithm, but if you run it forever, it will converge to the entangled value. The other algorithm is actually more interesting, and basically it's called non-commutative sum of squares, SDP hierarchies, or MPA hierarchies following this paper. So in 2008, there are two papers roughly giving you the same algorithm. And that algorithm is give you values that approaches to this commuting operator value from the above. So you have two algorithms and approaching these values, and we know that the star value, the entangled value, is smaller than the commuting operator value. In conclusion, the first algorithm would establish that MIP star is actually in RE, where RE is a complexity class as hard as the halting problem. Basically, if the problem has a yes answer, then you should have a Turing machine that eventually give you the yes answer. But if the answer is no, the Turing machine doesn't need to terminate. So you can see that algorithm 1 actually, if a problem in MIP star, meaning that you want to estimate the value of this entangled value, and you know that the value is high, then there will be an algorithm that eventually converge to that value. So in that yes instance, you do have an algorithm or a Turing machine to do that. What you don't know is when the value is low, and the algorithm it seems to run forever and it doesn't improve, and it doesn't give you anything. So the interesting connection now is that if Tsirelson problem has positive answer, like these two values are the same, then we have a very interesting conclusion. Basically, we have an algorithm to approximate the value of the entanglement value or the commuting operator value. Basically, you would alternating algorithm 1 with algorithm 2. You run algorithm 1 for some time, and then you switch to algorithm 2, and so on and so forth. And you can easily see that this will give you an algorithm, like a way to approximate this value within any given precision epsilon. So that would imply that MIP star is in R, which is a class that's intersection of basically it's decidable what the problem that you have an algorithm, no matter whether the answer is yes or no, you will eventually know by some Turing machine. So you would see that it is a contradiction to what we prove, because what we show is that MIP star equals RE, and RE contains undecidable languages, and for example, the halting problem. So that's the connection that we would know that Tsirelson's problem have negative answer if our proof is correct. So so after giving you the description of the problems, we are now ready to give you a more recent update on what we know about the class of MIP star. So there have been, the class was defined in 2004 in this paper of Cleve, Hoyer, Turner, Watchers. And in that paper, it was noticed that entanglement could be a problem, because if you start with a classically sound interactive proof system, then once you add in entanglement, there could be a problem for the soundness, because remember, entanglement would increase the value, and soundness requires that for no instances there should mean the value should be low. But then you increase, you allow entanglement, the value can increase, and in some cases it will cause problems, and that's called soundness problem. And actually you can see this happening, in this well-known example of Mermin's magic square game. You have here 9 variables, 6 constraints. Classically, you can think of it as a constraint system that you can turn it into a so-called constraint variable game, and it's a sound game, meaning that if this for the constraints are for all the rows you have even parity, for all the columns you have odd parity. And it's easy to see there is no solution to this system of equations, and classically correspond to that fact that the game has no perfect strategy. But if you have 2 EPR pairs and do clever measurements, you would always win this constraint variable game.
Zhengfeng,
yes.
Is this soundness condition at all related to contextuality?
Well, I guess it's a different setup. In our case, remember, the soundness is a requirement that when the prover is trying to prove something that is false, you should be able to detect that. The verifier should be able to detect that's a soundness condition. The provers are always trying to optimize the winning probability, and the soundness condition is that if the statement is false, you shouldn't be able to have a very high value or very high probability of winning. Now, when entanglement comes in, you would have a higher value, because using entanglement is always a resource, right? You have a higher winning probability. And that would mean that the classically sound interactive proof would become not sound, and so it doesn't make you an interactive proof. It doesn't really satisfy the soundness condition. So that's the connection. So it makes the problem interesting because you don't know whether having entanglement would make the class powerful or not. Even though here we pointed out have soundness problem, but you can imagine that the provers can also utilize entanglement and do something that is classically impossible. So it makes the question interesting. We don't have a good intuition of whether this entangled class would be harder or easier than the classical counterpart called MIP.
But the Mermin-Perez square, can that be restated in terms of quantum contextuality? Like a violation of classical contextuality?
Yeah. But for us, it's more like a game picture. Like we want to think of as a proof system where, like the first player, we didn't have time to tell you how the conversion from the square to the game works. So basically, Alice would have a random row, and Bob would have a variable from that row. Like Alice have a row or a column. Then Alice would need to respond on the values in that row or that column, and Bob would respond to the value he is given. And we check whether the constraint that Alice is sent is satisfied, and whether Alice and Bob, because like Bob's variable is from Alice's constraint, we require that they give the same value. And that's the so-called constraint variable game.
Okay.
And we think of this as interactive proof system for this fact that this set of equations don't have a solution, right? Because you can actually show that classically the value of the prover is lower than 1. You cannot always win the game, and that's something that we call soundness.
Okay, thanks.
Yeah. And so you can ask the questions. It's a very nice view to think of entanglement. Maybe it's a bug for interactive proof systems, or maybe it's a feature. And this big question of whether it is a bug or it's a feature. In some cases, it is indeed a bug. And like in two-player case with XOR games, the star version, the parity MIP star, is actually in p-space, while the MIP without the quantum entanglement with two provers and parity parity verification is actually equals to nexp. So we believe that p-space is much smaller than nexp. So when you have entanglement, the power actually decreases. And also in like unique games, in classical case, we don't know the power of unique game. It can conjecture be hard. But if you consider the entangled provers, actually the problem becomes easy. Again, this is like entanglement can cause the problem of the soundness problem, and sometimes it's like a bug. You cannot fix the problem if you only consider the special class of games. And then the second stage of this kind of research is people start to realize we can design entanglement-resistant techniques. Basically, the idea is that you design some construction so that the provers, like the dog scare, they cannot utilize entanglement because of this smart gadget that the verifier is using. And for example, you can have these so-called confusion checks enforcing the commutativity of the measurement. And also you can introduce, instead of considering two-player, you can use three-player setting. And because of monogamy of entanglement phenomena, we now know that they cannot behave as EPR pairs. And also there are more interesting, like there are tests or linearity tests or multilinearity tests, which are used in study of MIP classically, are shown to be immune to this entanglement attack very naturally. So you don't need to do any modification, it just works. So using this type of techniques, we were able to recover the NP hardness of non-local games. And so in 2012, Ito and Riddick, using this quantum version of multilinearity test, they were able to show that MIP is inside MIP star. So you can design for any NX language a protocol with entanglement. So in some sense, now you can see that bug is fixed because it is at least as powerful as the classical model. So the more recent stage of this research, the final stage is to study entanglement in powered particles. So we would study particles that are using entanglement in some essential way. And so the first breakthrough is for Simons and Wittig, where they give an interact particle for QMA, which is quantum analog of MP. And basically the idea is that we want to use quantum error detection code, or quantum error correction code, to encode the witness state of the QMA witness into multiple provers. And what I did is in that paper is to dequantize the messages. So it's actually a non-local game. So its messages are classical, and it's a protocol for this quantum analog of MP. Basically, we're able to go beyond this MP or NX classical barriers of the entanglement-resistant techniques. And later on, we would able to improve this, and a concept called compression of quantum intellectual proof systems are proposed. So basically, we would start from a protocol. We would come up with a small particle, but somehow simulate the behavior of the large particle. What we were able to show is like there's a parameter here called gap. Once the gap is decreasing, the complexity of this class would increase. So that the trade-off between the complexity and the precision. But this is already something interesting, because we don't see this kind of behavior in the classical setup when it's for MIP, because everything is discrete. We have a system of equations, and either you verify a constraint or not. You don't have this kind of behavior. And also, the implication is that if you are able to amplify the gaps are the soundness and completeness gap, then we would able to somehow argue that MIP star includes undecipherable languages, and there will be a big thing, because we know that if you can prove anything undecipherable in MIP star, then Tsirelson problem has a negative answer and column is false. Along a different line, I guess, using a different technique, William Slofstra is able to show this undecipherability for gapless linear systems. So you have like a system of linear equations, and you want to consider a quantum game version of that system. You want to know whether the system has like a perfect strategy or not. And that's shown to be undecidable. So like these two results are like here and here, they are all gapless. The gap is decreasing. What we want, or what we solve in this work, is actually we were able to maintain the gap and prove stronger results. So before this work, there are two interesting results that was mentioning. One is the paper by Anand and Thoma, where they proved QMA harness of non-local game with constant gap under certain conditions. And basically, they proposed a very powerful subroutine or gadget that we use called poly basis game. Basically, it's a very efficient self-test of poly X and Z. You would be able to enforce the players to share NEPR pairs and measure X and Z honestly and reply to you the result. Otherwise, they will be caught. So that's a powerful thing. And efficiency means that we don't even need to be able to address all this. The messages that we talk to the players to do this is much less than this number n here. And using this, and then John was able to first show that there's a Nix blower bound for MIP star, and that's, in other words, you can actually show that intelligent provers can prove more. Like if you think about the class that we define, MIP is about two provers trying to convince you something, and we're asking what can the provers convince you. And with entanglement, we actually can prove more because this double E is a double exponential. So we know that Nix is different from Next. MIP, the classical counterpart, equals to Next. So that's actually a separation. And from here, we actually have a lot of good results in that actually entanglement is a feature and not a bug. So in the main results of this work is the MIP star equals to RE, and basically you can interpret it as there's no algorithm that can approximate the quantum entanglement value, because that problem is as hard as the Hawking problem. Remember that we have this quantum set, this complex set of correlations. We want to optimize, like once you are given a Bell inequality, you are doing an optimization along this hyperplane, and basically what we proved is that this problem is as hard as Hawking problem, and the technique that we use to prove this is recursive gap preserving compression. We have already seen compression, and the results of NN and John is the first gap preserving compression. What we only need to do is actually try to make the argument recursive. So the consequence of our results, first we give a complete characterization of MIP star and its exact characterization. We know what exactly MIP star is. So the power is RE, and it's really unexpectedly powerful. And also we give a negative answer to Tsirelson's problem. Basically, it's also counterintuitive. Like it's actually the case that at least in certain tasks, infinite quantum systems cannot be approximated by finite ones. And it's a refutation of Kahn's embedding conjecture using the known connections that we know about Tsirelson's problem and Kahn's embedding conjecture in the literature. So in the rest of talk, I'll briefly give you an idea how we prove this result. So the overall idea is a compression of interactive proofs. So this is what we mean. We start with MIP star protocol here, where the messages are, the lines are thick, meaning that a lot of very long messages are being exchanged in that protocol. We'll come up with some new protocol where the communication is much efficient. You don't need to have very long messages, much short messages. And also the verifier is smaller. The running time of the verifier is much smaller. While the prover and entanglement remains at least the same, and even like we would use more entanglement. But remember that the definition of the game is from this part, like how the verifier samples the question and the answers and make decisions. Or that part, the definition of the game part is getting compressed. So that's a high-level compression lemma that we need. And so there's an algorithm called compress that when you input certain V, which is a verifier, in our model, we would consider the process as two things. First, it would sample the questions. So that's just some sampler. and then you make decisions once you have the answers. So there's a decider. So both S and D are Turing machines. And the algorithm compress with input V would output V sharp, a compressed version, such that the V sharp is like sub is like index of those. You can think of the index as the size. The size is much smaller. You start with 2 to the n for the uncompressed verifier. You would have index size n, but it tells you whether the value is high or 1 or it's less than half. Also, we have some conditions on the entanglement that this compressed verifier has to use. Like here, it actually uses more. Like at least the exponential larger version of the original verifier would require the player to use. So that's compression lemma. And the way that we use this compression lemma to prove our result is that we start with a Turing machine M. We want to understand whether the machine M is halting or terminating or not. And this is the way that we define the verifier called D hot. So first we will simulate the machine M for n steps, and it's index of this Turing machine. It's an input of this machine. And if M hots, then we accept. Because we know that M hots, and that's all we need to check. But if it doesn't hot, we run a compress algorithm, like we start to compress the D hot itself and come up with a pair of sampler and decider for the verifier, and we would accept if and only if the compressed verifier would accept. So intuitively, like in here, the compressed verifier is corresponding to the hot machine, hot verifier of 2 to the n steps, and so like in here, it would simulate M for 2 to the n steps, and if M hots, accept, and otherwise it would compress again. And then you check 2 to the n steps, but that's only the intuition. So the argument that to make this rigorous is something called Kleen's recursion theorem. Basically, what the theorem says is that the way that you write here is like you start with a description of Turing machine, but in that process, writing down the description, you actually use the description as a when specifying the Turing machine itself. Like it's like writing some like in high-level languages, we do this very often. Like you write some program and call this subroutine itself, but this theorem tells you, and this is valid thing to do even with Turing machines. Once we have this construction and the guarantees from the compressed lemma, you can show that if M hots, then the value of the hotting Turing machine is 1, and it doesn't hot, then the value is at most half, and that's something that's not hard to show once you have the compression lemma and the construction here. So as you can see, that the most difficult part then is to show the compression lemma actually works. And that's the most technical part of the paper. There will be 4 steps for the proof of the lemma. And the first step is very interesting, called introspection. So in the first step, the questions become smaller. We don't ask big questions. And then another important step is called the PCP step. So now we have this model where the questions are small, the answers are still big, and we use the PCP technique to reduce the size of the answers. If you still remember like what a PCP is, this is a natural thing for you to use, because the PCP is a very efficient way of checking the proof here. Like the verifier here, the small verifier is trying to check whether the big verifier is accepting, and we don't need to look at everything here. There's a clever way to check a very small number of bits and be able to convince yourself. So that's two major steps. And so basically this combination is like in a situation where the verifier is saying that I'm lazy. How about the two provers to come up with the questions yourselves, answer them, and prove to me that I would have accepted the questions and answers. And I guess that's a very interesting idea. And in more detail, what you would actually require the introspection to achieve is to you start with two functions, LA and LB, and that's the two functions, so that the LA applied on Z and LB applied on Z is a question distribution that we want, and when Z is uniformly random. So Z is like a random seed, and this random seed will come from Z measurement of half of DPRs. We want to have the situation where when we send this special command intro A to Alice and intro B to Bob, they would do honestly what introspection is meant to them to do. Basically, the player would reply with Y and A, where Y would be this LV applied on Z, and the answer A is the answer of the original game when you have the question Y. So the player should come up with the question and answer themselves. And of course, the difficult part is how can you how would you be able to ensure that the provers follow the command? And that's where we use the rigidity or the efficient self-test of polybasis. So basically, we already have like from the polybasis test, you can command the players to measure honest Z measurement, and so that's easy. You just introduce an intermediate step called sample, and in sample you would measure everything, but only the Y that is being processed, but also the four random seed, and then you check whether this Y here and Z here are related by a linear function LA, and that works. But that's not only half of the story. And an important part is that how are you able to ensure that prevent Alice from learning extra information of Z? Remember, in the model of two-prover interactive systems, Alice doesn't know Bob's question, and Bob vice versa. Bob doesn't know Alice's question, and that's essentially a thing to have. But now look at the situation here. Like looks like this Z is coming from the EPR measurement, and seems like both Alice and Bob can have access to that information, and that's something that we want to prevent. And basically, what helps us is essentially quantum, and we would use Heisenberg uncertainty principle to achieve this. So sometimes we would ask the players to measure X to erase the information in the Z basis, so that the players has to follow the strategy honestly without learning extra information while playing the game. So that's a crucial idea, and that's how you achieve this by introducing a type called hide and check whether the garbage or hiding part is correctly measured in the poly X measurement. So that's a way that we can do introspection only for linear functions. And skip this. So the next difficulty is we have to encounter is linear functions are not enough. Basically, linear functions are giving you the ability to measure X and Z, and we would also sometimes require the distribution to have more interesting structure. Sometimes like the linear, the line point distribution would have a distribution that is cannot modeled by linear functions. but if you look at the conditions or constructions of the line point distribution more carefully, it is actually linear once you have conditioned on one of the information called V. So it's basically, you can have a chain structure where you generalize this linearity with some conditioning. It's like going beyond the Clifford group. You need something that is beyond only X and Z. You would add conditioning. And in our case, you would come up with a definition called conditional linear functions. And the good thing is that it's almost linear in each step, and it's chained conditioning. And you can argue that it works, meaning that you can introspectively sample the distribution in that general case. So the good thing about the CL functions, it makes our the modeling of distribution much easier. The power is that you can almost all distributions that we have can be modeled as CL distributions, and we can introspectively sample this distribution using similar techniques that we did for the linear functions. And so that's introspection, and as we said, you can do answer reduction, and it's much like what we said before. You just use a PCP, and basically the verifier would only ask the prover to send the PCP proof to make sure that the big decider would accept. Some remarks, I guess, like in retrospect, in the application of the PCP technique require us to actually have a very special structured measurement called commuting, even though like in the model where Alice and Bob are separated, and we would ask them to measure commuting operators, because in our correlation step, we would move Bob's measurement to Alice's measurements. And it's also the reason that we were not able to work to apply this PCP technique when we used quantum error prediction codes, because in that model, local prover don't have much information, or they have is random information, and information is included in the parity of the provers. So that's another reason that it's really hard to apply the PCP technique. We only know this after Anna and John's work. And also the universal sampler, like remember what we had in the compression theorem, the sampler is already like a fixed point of the compression procedure, and that's interesting observation, and it's enabled us to make arguments simpler, and it's a reason that CL functions has been helping us. So to conclude, we prove recursive gap-preserving compression of normal form two-prover one-round protocols, and there's to applying this compression lemma and Klean's recursion theorem, we were able to prove that halting problem is in a problem in MIP star, and the other part follows from the algorithm one that we show you. So that gives us the equality of these two classes, and based on known connections, we give negative answer to both Tsirelson's problem and the Kahn's embedding conjecture. There are a bunch of open problems. One is, how can you simplify the proof? The current proof is 160 pages, and it's hard to verify, to be honest. Also there's a class called commuting operator version of the MIP, and we conjecture that it is equal to QRE. That's something that we are working on, and there are some other open problems like implicit constructions for counterexamples to the constant embedding conjecture. So that's some feedback that we have from both comms, from Com and Tsirelson. So it's nice that the results is appreciated by the pioneers of the area, and it's like what Tsirelson said, it's very nice to see that connection between computer science and quantum information to mathematics and physics. Okay. A little bit over time.
Thank you, Zhengfeng. Thank you very much. How do we do a big applause via Zoom? I think from my perspective, this worked really well. Let's go to questions. Maybe before I do that, it's really amazing. We had like at peak almost 50 people from a bunch of different institutions. I think participation has been really good. Let's see if we also get a lively Q&A session going. Please, who has a question? You have to unmute yourself, obviously. No questions. I find that surprising. Because while people look for the unmute button. Okay, I see people unmuted. Sasha, do you have a question?
Oh, yeah, well, so just a fairly naive question about the implications that this has in terms of the Tsirelson problem. Mm-hmm. Like, I mean, does this, I mean, well, I mean, it is sort of an open-ended question. Are you able to talk a little bit about like what implications this has about the mathematics of describing quantum systems, or is this purely an approximation result, like a computing result?
Yeah, that's a very nice question, I guess. So in quantum information, we have been used to use the tensor structure to define things like entanglement. And I guess in quantum field theory, people model the theory using commuting operators. So the question is whether it is actually like the games we have where you can separate these two setups, like commuting operator and tensor structures. Whether the separation is physical is a big question. Meaning that whether you have like some quantum field theory where the operators that we measure in the protocol can be realized, so that there's no finite dimensional approximations, and whether you can set up some sort of Bayes inequality-like experiments. And I think that's a very interesting question. But as far as I know, there's like we don't have any candidate that any quantum field theory that can support our measurement. Basically, there are like, even though people don't require tensor structure in the modeling, there are extra conditions like split condition properties in that model would imply like tensor structure in the end. So yeah, I don't know, like, but it's an interesting question to explore, yeah, whether it actually makes a difference to think about. It is a physically relevant question whether you should, like, which model is the most accurate way to describe quantum physics is I think it's a big question.
Thank you.
And from
Nathan, go ahead.
So I guess you were touching on this idea already in your answer, but I wanted to ask you about, so effectively what you've done is you've shown that there is a class of quantum tasks that is somehow significantly more complicated than you might expect, or at least significantly more complicated than the equivalent classical task. And I guess how the question comes, how do you realize that? How can you show that? And so I realize that you already touched on this a bit, but do you see, I mean, for example, with the question of non-contextuality, for a long time, we had like the Koch and Specker theorem, for example, which was just a yes/no thing, which was basically kind of like the GHZ entanglement condition, where it's basically you can show something that like it's a yes/no, it's impossible classically, but there's quite a lot of development to get from the point of this yes/no question to the point where you could say, right, here's an experiment I can do where there is a limit, like there's some sort of inequality where I can't get past this inequality. And so deriving some sort of contextuality, non-contextuality inequality where you could actually go past a threshold and even in an experimental situation, define errors and so forth so that you could say, right, I went over the threshold by a certain number of sigma. Do you have any sense of what direction you would need to go to try and be able to demonstrate the power that entanglement gives you in this context?
I'm not quite sure, like, if I understood your question, but like, we have everything, like the concrete construction of the inequality, although it's really complicated, but it's something that you can write down. But the question is whether this result is purely mathematical result or it has physical relevance. That's something that I don't know. Meaning that we are requiring the operators in the system to satisfy a bunch of constraints, and whether you can have quantum systems that it can realize all these operators, it's unclear to us.
And is this to do with the link between the finite dimensionality and the infinite dimensionality? Is that where the challenge is?
Not necessarily. Like because the good thing about the game is it's some finite structure, right?
Right.
You are having a question set, answer set, and a decider. That's all finite. You can write it down. That's some, like, maybe within a page I can, or within 1 megabytes I can encode this game on computer. It's something finite. But then the strategies of the game can be more complicated. Like you are checking a bunch of operator constraints, and basically what we are saying that there should be no finite dimensional solutions. There's no matrices for the constraints, but there are solutions when the operators are in infinite dimensional Hilbert spaces, and we just don't know how you can physically implement these operators because they are infinite dimensional and we don't have.
Right, so it's the realization of the measurement part of the protocol somehow that, or the strategy that you introduced, that where it's that's where the complexity is.
Yes. Somehow it's like an indirect argument because what we show is a compression procedure. We show that the boundary of this correlation class, correlation set, is where is it? So the boundary of the quantum set is so complicated that you cannot even optimize over the set. And from that, we would deduce that there are differences for considering finite dimensional operators and infinite dimensional operators, because
Sorry, I lost you for a moment. I don't know if you're back. So do we understand this as if there's a classical problem and so that it's very easy to write down the game, but for most instances in the game, you do not expect to see a quantum speed up or a quantum improvement. So actually getting to finding a particular instance where there is a difference between the quantum speed up, between the quantum case and the classical case, that's really hard to find.
Well, quantum and classical are easy to find. That's Bell inequality, right? You can find it in 2x2 systems.
No, I mean in this particular example.
In our case, yeah, I think like the dimensions and like, I don't have like, on top of my head, I don't have like estimates of like the size of the question sets and answer sets, but they are huge.
Okay,
yeah.
Thanks.
Okay, unless there's a very pressing question, I think we have to stop here just in the sake of time, because it's now later than 4:15. So no one is screaming for pressing questions. Then I really like to thank Zhengfeng again for this excellent talk and for being the very first person to deliver that Zoom seminar in the School of Physics in CQC2T. We'll keep this going. I think this is working, which is outstanding. So thank you all. There's the little reaction applause button. Go for that.
Or just unmute.
Yeah, well, unmute. That's even better. Great. So unmute all, and off we go.
Thank you.
Thank you.
Cool. Thank you. Bye-bye.
Bye.
Bye.
Bye.